Good morning all of you. Welcome back to course Database Management System. So our today's topic is Introduction to Btree and B+tree indexing. So in the previous video we discussed about types of indexing. So we understand that there are two major categories that we can use to classify our indexing. First one is whether it's a single level indexing or it's a multi-level indexing. That is a thing. Then the second major category is what? Whether your file is sorted or not. Whether your file is sorted or not. Suppose your file is sorted, then there are two major types are there. One is primary indexing and clustering indexing, and suppose your file is not sorted, then you have to go for secondary indexing. But we have first category. What is that? Single level indexing and multi-level indexing. So we discuss about dense index and sparse index. So dense index and sparse index, these are the examples of single level indexing. Okay, and then we discuss about multi-level indexing. So what is multi-level indexing? In case of multi-level indexing, we can have more number of layers. So when you should go for single level indexing and when you should go for multi-level indexing. This is what a very important thing. So single level indexing is useful when you have limited amount of data, but when your data is increased tremendously, at that time single level indexing is not useful. At that time you have to use multi-level indexing, because the thing is very simple. Suppose the size of your indexing file is very large, then it takes lot of time to search index file itself. That's why we cannot increase the size of index file up to after some specific limit. So at that time what we are going to do, we are going to create one more level. So multi-level indexing is useful when a huge amount of data is there in our database. Means when our data is limited, we can make use of a single level indexing. So in that case we have choice, either we go for dense index or sparse index. But when our data is increased tremendously, at that time single level indexing is not beneficial. The reason is very simple. Suppose the size of your index file is very large, then it takes lot of time to search index file itself. And our main objective of indexing is what? To reduce the accessing time. Okay, to reduce the accessing time is a main criteria. Okay, to reduce the accessing time, for that purpose we are using the concept of indexing. Okay, so this is what our main criteria, to save a time of accessing a particular record from the table. Okay, so in that case we should go for a multi-level indexing. So in the last video I have shown you the structure of multi-level indexing. This is what a main structure of multi-level indexing. So in multi-level indexing, what we have the actual table which is divided into number of data blocks. In each data block we can store n number of records, and for this particular table we are storing the indexing. So this is inner index and this is what a outer index. So multi-level indexing is useful when we have tremendous amount of data. So today we are going to discuss about type, or you can say concept which supports multi-level indexing, that is Btree and B+tree. So Btree and B+tree, you can say it's a kind of multi-level indexing, because in this case we can have multiple levels of index. Okay, in this case we don't have only single level. In case of Btree and B+tree, we can have multiple level. So very first thing that I'm going to clear to you, that Btree and B+tree is a kind of multi-level indexing, because now we are going to discuss multi-level indexing to deal with a huge amount of data. This is what our main objective. So for that purpose, first of all we try to understand what is Btree. So as its name suggests, Btree means what? It's a balanced tree. Btree is nothing but a balanced tree which keeps your data in a sorted order. This is what the important thing about Btree. B stands for balance. Btree is a balanced tree which stores their data in the sorted order. So there are few properties are there for Btree that you need to understand. But before discussing the property, we should know what are the basic terminologies of a Btree. So in case of a Btree, you find node. This is what a single node is there, and this is what a pointer. So in this particular node we have total 3 pointer, pointer 1, pointer 2 and pointer 3. So there are 3 pointers are there in this particular node. And what is that 5? 5 is nothing but a key. So this is pointer 1, pointer 2, pointer 3, and it consists of only one key. Before discussing the property of Btree, you should know what are the basic terminology that we are going to use to understand the concept of Btree. So very first terminology is node. So what is node? This is what a node where we are storing the key as well as the pointer. So in this node we are going to store 3 node and it stores the 1 key. So from this, what is your understanding? How many key can be present in a single node? So formula is very simple. So in this case, a number of pointers are 3. And what is the maximum number of key that it can hold? 1 and 2. So from this we can understand every node can have maximum how many n minus 1 keys, where n represents the number of pointer. Suppose somebody has shown you the particular node and they will ask you just tell me how many keys we can store. So simple formula you can use. It can store n minus 1 keys. Maximum n minus 1 key can be stored in a single node, where n represents the number of pointers. So pointer of what? In case of Btree, that pointer is pointing to record of a table also, as well as it will point to child node as well as the internal node. So in case of a Btree, that pointer represents the address of a record present in the table or address of a internal node, okay, or address of a child node. So this is what you need to understand. And then this is an example of Btree. So here level 0, level 1, level 2, they are called as a leaf node. Leaf node do not have any particular child. Okay, leaf node are that node which are present at the lowest level of the tree and which do not have any child. So this is what your leaf node, and this is your root node, and they are called as a internal node. Root node, internal node and leaf node, and these are considered as a level 0, level 1, level 2. And what is the order of the tree? Order of the tree is nothing but a maximum number of child that particular tree can have. So in this case, suppose we consider only this part. So in this case, how many children that it can have? 1, 2, 3. So for this particular node, we can say that order is 3. So order of Btree can be evaluated by using maximum number of children can be created for that particular node. So these are the basic thing that you should know. What is n? N is nothing but a number of pointer. How many keys it can have? It can have n minus 1 number of keys. Now we just try to understand what are the properties of Btree. Very first property is each node has at least n by 2 to n child. Okay, each node have n by 2 to n child, where n is a maximum number where n is a number of pointers per node. Means for one node, how many children it can have? N by 2 to n. N by 2 to n children can be there. So for this node, n by 2. So what is the value of n? 1, 2, 3. So n by 2, just consider 1.5. So either you can consider 1. So minimum it can have 1 child and maximum it can have n child. So this is what a first property. Each node in a Btree can have n by 2 to n child, and n represents the number of pointers. So in this case, pointers are 3, 1, 2, 3. So n it can have n by 2 children. That means it can have minimum 1 children and maximum it can have 3 children. This is the first property. Second, all leaf node will be at the same level. So here you can observe all the leaf nodes are present at the same level. Okay, this is the meaning of this. All nodes should be present at the same level. Next thing is, all leaf node can contain maximum n minus 1 keys. So I already told you that every node in Btree can hold maximum how many keys? N minus 1 keys. So it may be leaf node or any other node, but we are specifically talking about leaf node. So in case of leaf node, suppose this is what a leaf node, so it can have n minus 1 number of keys. And last property of Btree is what? For each non-leaf node, left subtree can have key value less than non-leaf node, and right subtree can have value greater than non-leaf node. So we are talking about this for in non-leaf node. So we can say this is non-leaf node because I told you there are three category: root node, internal node, and leaf node. So this is also called as a non-leaf node. So how many what it can have? It can have value less than this, and here you can see this is again another example. So here what we can say, 2 and 3 these are less than 5, and 7 and 8 is greater than 5. Okay, means in case of Btree you have to always make sure that left tree consists of a key which is less than the non-leaf node. So in this case non-leaf node is 5, so 2 and 3 is less, and 7 and 8 is greater than this. So this is what a last property of a Btree, that left subtree can have value less than that non-leaf node, and right subtree can have value greater than that non-leaf node. So here 7 and 8 is greater than 5, and 2 and 3 is always less than 5. Similarly for 9, 7 and 8 is less than 9, and 10 and 11 is greater than 9. So these are the properties of Btree. So I hope you understand the concept of Btree. Now we take an example where I can show you how Btree can be used to index or record in case of a database. So just imagine a situation. This is what our bank table, which consists of this many record, and we have just created our index based on the account number. So what type of index we have created? Primary index, because in this case data is sorted. Okay, and indexing is created on what? Based on the primary key. So we can say that we are using the concept of primary indexing. In case of a clustering indexing, index is created based on what? Non-primary key or non-key. So in this case account number is a primary key, name and balance is a non-key attribute. Okay, so in this case imagine a situation, we have just created an index based on the primary key account number. So how Btree can be used, and this is what a structure of Btree. Here you can see this is a node. Okay, this is what a node, it is pointing to left child, this is pointing to right child. Okay, and this is pointing to right child, this is pointing to left child, and here leaf node or non-leaf node can also hold the record pointer. This is what the main characteristics of a Btree that you should understand, because after this we are going to discuss about B+tree. So one major distinction between Btree and B+tree is that in case of a Btree, non-leaf node can also hold a pointer to record of the table, but in case of B+tree only leaf node can hold a pointer for record of the table. But in case of Btree, non-leaf node can also have pointer which is pointing to record of the table. That's why it required additional node in case of a Btree. Okay, so here suppose imagine situation, I need to find account number 7. So how can I find it? In this case you can find there is a pointer which is pointing to this particular 7. Suppose I need to find 5. So here you can see this particular pointer is pointing to record 5. So in this way we can point it to every record present in the table. But what is another thing that you need to understand? In case of Btree, not only leaf node but non-leaf node can also hold a pointer which is pointing to every record of the table. So this is what the concept of Btree. Now next we discuss about the concept of B+tree. So what is B+tree? So what is the main distinction that you observe between Btree and B+tree? In case of Btree, so in case of B+tree, plus sign is there. Plus means what? Some additional thing will be there. So first try to understand what additional thing is present in a B+tree as compared to Btree. I just told you what is a major difference. In case of Btree, we are storing our pointer, means we can store a pointer to data not only in a leaf node but also in a non-leaf node. But in case of B+tree, you can see only we are storing pointer to a record in the leaf node only. Means in this case non-leaf node cannot point to a record present in the table, but only leaf node can point to record of the table. So this is what major difference between B-tree and B+tree. So B+tree is a variation of B-tree. We can say it's an advanced version of B-tree, because plus means what? Some additional thing will be there. So this is what a additional thing. So what problem we face in case of B-tree? In case of a B-tree, we are non-leaf node also storing the address for the record. So unnecessarily it occupy the space. So what we have done in case of B+tree, we have just removed this pointer from non-leaf node and we keep in only leaf node. So this is what a modification that we have done as compared to B-tree in a B+tree. So B+tree is a variation of B-tree in which each node contains key while only leaf node contains key and date. So meaning of this what? This non-leaf node contains only pointer to key, pointer to next child, but here leaf node consists of key as well as pointer to record present in the table. So this is what the main thing you should know about B-tree and B+tree. Next, try to understand the properties of B+tree. So what are the properties? All paths from root to leaf are of same length. So here you can see these are the leaf node. So leaf node 1, 2, 3, 4. So from, and this is what a root node. So from root node to leaf node, their path is of same length. Okay, their path is of same length. So this is what a first property. All path from root to leaf are of same length. Then each node that is not a root or leaf, each node that is not a root or leaf has n/2 to n child. That means we are talking about what? Non-leaf node. So in this case it can have n/2 to n number of child. So it can have minimum 1 child and maximum how many child? 1, 2, 3, 4. And how many pointers are there? 4. N represents what? Number of pointer. So this non-leaf node can have either 1 child minimum and maximum n child. So this is what this property. Then leaf node has between n-1/2 to n-1 key values. So in this case this is what a leaf node, n 1 2 3 4. What is the value of n? 4. How many number of minimum keys? Minimum keys is 1, maximum keys are n-1. So okay, so maximum how many key it can hold? n-1, because 1 2 3 value of n is 4. How many keys are there? 1 2 3, so n-1. Then internal node is used as a placeholder to guide the search. This is an internal node, and this they are only used for guiding the search. Okay, they are not holding any kind of pointer which points to record present in the table, but they are only treated as a guidance. Okay, they are providing the guidance which helps to search the particular value in the B+tree. Then all leaf node links together by linked list. So in this case, one more thing, every leaf node consists of a p next. P next means what? Pointer to next node, because this is this node, this pointer is pointing to next node, this pointer is also pointing to next node. So all the nodes present in the leaf all the node present in the leaf level are connected with each other by means of linked list. That means every leaf node contains the pointer which points to next node, okay, which is present at the leaf level. Means leaf node not only consists of pointer pointing to record present in the table, but it also holds pointer to next node present at the same level. So this is what this all leaf nodes are linked together to form a linked list. So this is what an example of B+tree. Here same example we discuss in case of B-tree, and same example we are discussing in case of B+tree. So what are the differences that you observe? So in case of B-tree we have only two level. This is level 1 and this is level 2. But in case of B+tree we have 3 level, 1, 2, 3. Okay. Why this thing is happening? The thing is very simple. In case of B-tree, non-leaf node can also hold pointers pointing to record present in the table. Okay, so in case of B-tree, what is your observation? Non-leaf node can also hold pointer which pointing to record of the table. But in case of B+tree, only leaf node is having a pointer which points to record present in the table, but internal node do not have the pointer which points to record present in the table. But internal node contains the pointer to only child. This is what a major difference between B-tree and B+tree. So this is what a structure of B-tree for same table, and this is what a structure of B+tree. So what is a major difference you need to understand? In case of B+tree, only leaf node can consist of pointer to record present in the table, but in case of B-tree, non-leaf node can also hold pointers pointing to record of the table. Next, at the last, we try to understand what are the major differences that we observe between B-tree and B+tree. Very first difference, in case of B-tree, it can store key and data in internal node or leaf node, but in case of B+tree, it can store key and data only in the leaf node. This is a major difference that you need to understand. Then no redundancy of search key in B-tree, but in case of B+tree, redundancy of search key. So here you can see 5 is repeated, but in case of B-tree, there is no repetition of key. Intentionally, in case of B+tree, we are repeating in order to guide the search. Okay, then additional pointer is required in case of B-tree, but in case of B+tree, no additional pointer. What is a additional pointer? This is what a additional pointer that we required in B-tree, but which is not required in a B+tree. Then insertion of new node is somehow complicated in B-tree as compared to B+tree. Then similarly for deletion of non-leaf node is somehow complicated in B-tree as compared to B+tree. Then data can be searched before reaching to leaf node. Here you can see, suppose I need to find 5, so whether it is necessary to visit the leaf node? No, 5 is present in the root node, so you can find the data itself. But suppose this is the case in B+tree, it is necessary to reach to leaf node. Suppose I want to find 5, means here this 5 is of no use because it doesn't contains pointer to record, but only leaf node have pointer to record. So in that sense I am telling you data can be searched before reaching to leaf node, but here data cannot be searched before reaching to leaf node. Then B-tree require less number of node. Here you can see how many node, 1 2 3 4, but in case of B+tree 1 2 3 4 5 6 7. So in case of B-tree we required less number of node, and B+tree we required more number of node. Our data is same. Here you can see for B-tree data is same, and for B+tree also data is same, but B+tree required more number of node because here few node act as a guider. Okay, it act as a guide for search. That's why in case of B+tree we required more number of node. And at the last, it's difficult to traverse key sequentially as they are stored in a non-leaf node. Sorry, they are stored in a leaf node as well as a internal node. But in case of B+tree, it is very easy to traverse because in case of B+tree we are storing all the key and data in the leaf node. So from this leaf node you can easily traverse to any record of the table. So this is what a important feature of a B+tree. Okay, in case of a B+tree you can easily reach to any record of the table because all the keys and values are present in the leaf node. But this is not the case in case of B-tree. In case of B-tree, few keys are present in leaf node and few are in a non-leaf node. So these are the major differences between B-tree and B+tree. So I hope you understand what is B-tree, what is B+tree, how B+tree is different from B-tree. So in the next video we are going to discuss about how to solve a numerical based on a B+tree. Thank you.